Hi guys, it's Miss Griffin. We're taking a look at Unit 3, Skill 6, and we are talking about line symmetry and rotational symmetry. And so our first topic is the line symmetry. Your essential question says, how can we determine if a figure is symmetric for both line symmetry and rotational symmetry? So line symmetry is a line that divides a figure into two congruent images, and lines of symmetry map a figure onto itself. So it's like you're creating a mirror image. I'm recording this video at my parents' house, and today I've got little Rocky joining me. This is my mom and dad's youngest cat. They have another kitten that's only 6 months old, but this is Rocky, and he is a sweet little, I don't know, probably 2-month-old little kitten. So he's hanging out here next to me. So back to line symmetry. We are taking a look at these figures and drawing in lines of symmetry for the following figures and trying to figure out how many lines of symmetry each figure has. So if I think about wanting to make a square symmetric by cutting it, I'm going to cut it maybe down the middle vertically. So that's one line of symmetry. I could also cut it down the middle horizontally. That's a second line of symmetry, because the top part would map onto the bottom part if I were to fold it over that line. However, I can also do the same for the diagonals of a square. This is my third line of symmetry and my fourth line. So a square has 4 lines of symmetry. Okay, so again, you're thinking like, can I fold it and it matches up on both sides? Can I fold so that it matches on both sides? Okay, so then we're taking a look at an equilateral triangle where you know all the sides are equal. And so I definitely can split down the middle vertically. I can take another vertex and go through the middle, and the third vertex and go through the middle. So an equilateral triangle has 3 lines of symmetry. Now for a rectangle, I know I can split it down the middle in half right here, because again, this left side would fold on top of the right side, and the corners, the vertices, would match up, mapping onto one another. And then I can definitely go horizontally. Top would fold onto the bottom, but I cannot go diagonally. And the reason I cannot go diagonally is because if I fold it along that diagonal, this piece here would not map onto this piece here. If you don't believe me, take a piece of paper and fold it along the diagonal. You would see that this vertex does not map onto this vertex. So that cannot happen. So a rectangle actually only has 2 lines of symmetry. And then we're moving forward into a regular hexagon. Regular meaning that all sides are equal, hexagon having 6 sides. So I can split it down the middle. I can split it along 2 vertices, down the middle, 2 vertices, down the middle, 2 vertices. So when I count this, I want to make sure I don't double count. Don't double count lines of symmetry. So I have 1, 2, 3, 4, 5, 6, but if I were to count this line here, it's the same as line number 1. So I'm not going to count it a second time. That means a regular hexagon has 6 lines of symmetry. The next one, isosceles triangle, has 2 sides congruent. Isosceles, 2 sides congruent. And so I know that I could definitely split this down the middle, right? Because this vertex would map onto this one, and this vertex would map onto this one. But I don't think that I can split it horizontally. If I tried, it would look like a line going this way. And you could see that the vertex at the top would not map to the vertex on the bottom because they are in different positions. They would not make a mirror image if I drew a line through here. So trapezoid, that's isosceles, actually only has 1 line of symmetry. And now for this scalene triangle, all sides are different, 0 congruent sides. So if there are 0 congruent sides, well, I can't cut it down the middle, can't cut it down the middle, can't cut it down the middle through a vertex. So in fact, there are, if I can erase all of this, 0 lines of symmetry. Now we're going to apply it to a graph. It says in the diagram below, a square is graphed in the coordinate plane, a reflection over which of the following does not carry the square onto itself, meaning does not map the square onto itself. So I've got this equation, x equals 5, and I'm going to use colors here to help us see this because we're going to be graphing 4 different lines. X equals 5 means go to 5 on the x-axis and draw the line straight up and down. So if I were to take this square right here, all 4 vertices, and reflect it over that purple line, I know that the 2 on the line would stay, but then these other 2, like this one on the far left, would flip somewhere over here. The one on the far left bottom would flip over here. So if I were to draw this in, the square did not stay in the same position, meaning it did not map onto itself. So I think that that's the answer, but we're going to go through each option to figure out whether or not we're correct. Y equals 2 I'm going to do in green. So I go up to where y is 2, and I draw the line horizontally this time. So here's my original square, remember. And if I look at that square with the green line going through it, that green line cuts it in half, meaning a reflection over that line carries the square onto itself. It makes it a mirror image. It makes it symmetric. So that's another way to say this, which does not make a line of symmetry on the square. Okay, so then we've got another one, y equals x. So that has a starting value of 0, and it goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, so on and so forth, as it becomes the diagonal of the square. Remember up above we said diagonals of squares are lines of symmetry, and therefore it would map the square onto itself. Now in this next one, x plus y equals 4, it looks a little funky, so most students automatically choose that one because it looks different than all the others. However, if we get it in y equals by subtracting x, then we have y equals 4 minus x, meaning we start at positive 4 on the axis for y, and we go down 1 over 1 because it's a negative x. And you can see that this starts becoming the opposite diagonal. And again, diagonals are lines of symmetry on squares. And so therefore the one that does not carry the square onto itself is choice 1. If you flip it over and take a look at the back side, sorry about that big line, you will see that we're going to start talking about rotational symmetry after we get one more problem with line symmetry. So here for line symmetry example 3, it says reflecting over which line will map the trapezoid onto itself. So it's the same process, take colors and start drawing the lines in, seeing which one will map the square onto itself, or which one is a line of symmetry. So y equals -1, I go to -1 on the y-axis and draw the line horizontally. That does not work, right? If I fold the trapezoid along that line, it would not be symmetric. X equals -1, so I go to -1 on the x-axis, and it looks like that might be it because I'm 2 away from this vertex, 2 away from this vertex, 5 away, 5 away, so it looks like it might be symmetric, but let's check the other ones. So for y equals 0, this is really the x-axis. So if I draw a line on the x-axis, cutting through that trapezoid in that way, it would not be symmetric. And one more, x equals 0 is the y-axis, because everywhere on the y-axis x is 0. That does not cut this trapezoid in half, such that each side would map onto itself. And therefore, number 2 is our choice. So next we've got rotational symmetry, and that is relating to the number of degrees that an object is rotated around a point, and usually that point is the center. Let me just write that in. Around a point such as the center of that shape, so that it maps onto itself. And we divide 360 by the order, which is the number of times the shape can be rotated to look like itself. Or the order could also be the degrees of rotation, or the number of sides. And we'll see this play into an example in just a minute. What is the degree of rotational symmetry for the regular pentagon about point F? So if you think about this pentagon has 5 sides. And we know that the total number of degrees in any full rotation all the way around full circle is 360. I know that it has 5 sides and it's regular where all sides are congruent. Then that means that I can take 5 turns all the way around. And so now we have 360 divided by 5 to give us 72 degrees for each individual turn so that it looks like itself. Meaning if I turn and I take A and map it onto E, that was a turn of 72 degrees. So that whole figure would rotate 72 degrees and it would look just the way it does right now, except that each letter would be shifted. So now it says what rotation around point F would map B onto D. And remember with rotations that we always go counterclockwise. So here's D, here's B. I have to map B onto D. So I gotta move towards the left. That's 1, that's 2, and that's 3 turns here. So I'm taking 72 degrees times 3 turns, for a total of 216 degrees. So it would take me 216 degrees to turn from B to D. Now the next question is actually something that you might see on a Regents exam. It says which rotation about center F would map the regular pentagon onto itself. So had we not done the first 2 steps, we're going to treat this as if we had not, so that you can see what the process would be if you were starting this problem fresh. So we have a regular pentagon, meaning 5 congruent sides. A full rotation is 360, remember, so we divide and we get 72. Right? You've already done that, but we're pretending you hadn't. So I know that 1 turn is 72 degrees. So this is going to be the number of turns, and this is going to be the degrees. 1 turn is 72 degrees. 2 turns is 144 degrees, because I multiply it by 2. 3 turns is 216 degrees. 4 turns is 288 degrees. 5 turns, and I could keep going, but what I'm looking for is one of these numbers to be divisible by 72. So which number does 72 degrees go into? So you can either make the little table like I did, number of turns and then the degrees, and find out, oh, 72 goes into 288 4 times, or I could have taken each number 108 divided by 72. Nice number, meaning no decimal, like a whole number, then I know that that would be my choice. But this one is not equal to a whole number, so I know that 108 is not my answer. Personally, I like this little table that I'm making, multiplying 72 by the number of turns and finding out which one works. Might be a little bit more work, but I think it's the easier option. In example 6, it says which regular polygon has a minimum degree of rotation of 60 degrees to carry the polygon onto itself. So they name all of these polygons, but we have to know how many sides each one has. And so we're actually going to first make a list off to the side in your little column over here of all shapes and their number of sides. So a triangle has 3. Quadrilateral has 4. Pentagon, 5. Hexagon, 6. Something called a septagon has 7. Octagon, like an octopus, has 8, just like an octopus has 8 legs. Nonagon, Nonagon, has 9. And decagon has 10. Decagon, like a decade, 10 years. These you have to memorize. They are never given to you, and this example 6 was a problem on an exam at one point. So if you have it memorized, your life will be easy. If you don't, then life will be difficult. So whenever I see a problem like this, octagon, I have to write 8 because I know that it has 8 sides. Decagon has 10. Hexagon has 6. Pentagon has 5. Again, those just came from our list, and I've already memorized them myself. And I know that any figure can have a full rotation of 360, but I know that I want to figure out which one has a minimum rotation of 60. So I take 360 and I divide it by the degree of rotation. Unlike before, I took 360 and divided by the number of sides. This method works both ways. Okay, so if you want to find out the number of sides, you divide by the degrees. If you want to find out the number of degrees, you divide by the number of sides. When I divide, I find out that it's 6, and therefore choice 3, hexagon, is my answer. Make sure that you do your practice before you move on to any CFUs, so that way you can get some feedback if you're making mistakes before you take your little quiz. Let us know if you have questions. Otherwise, adios.